Okay, so let's take a look at another potential fusion reaction, and this is an example from the book. And although the previous reaction where we fuse two deuterium nuclei together, it does occur in stars, but actually the much more common reaction in the stars is the following reaction. We simply take 4 protons and we fuse them to produce actually quite an array of particles on the other side. We do end up with helium. We end up with 2 of these particles. I want you to think for a second what particle this is. We end up with 2 neutrinos, and we actually do end up with a gamma ray. So quite a complex reaction. Now the reason why this reaction looks so complex is because it actually takes place in several steps. You can't fuse together 4 protons. The way that it works is you fuse 2 protons together, then you fuse a third in a separate step, then you fuse the 4th one in the final step. So it's actually several steps, and along the way you end up releasing these particles. So these particles don't come out all at once, but instead in steps, and if you collect them all together, these would be the particles that come out on the right hand side. These particles on the left hand side are just protons. They do not have electrons. On the right hand side, this helium nuclei will also not have electrons. So we need to make sure when we use the mass of the hydrogen and the mass of the helium, we don't account for the electrons, because there are no electrons. In fact, there are no electrons here either. These are not electrons. Instead, these are what are referred to as positrons. These are the antimatter particle that's the equivalent of the electron. So notice there's no negative sign there. So keep in mind, these are positrons, not electrons. And then since these are the antimatter particles, these are just regular neutrinos, not antineutrinos. It's a minor point. You really don't need to worry about whether you have the bar over or not. You can just simply put the symbol nu for the neutrino. And in this case, and during one of the steps, they actually do produce a gamma ray. So let's go ahead and take a look at the mass. Since these are simply protons, I'm not going to use the atomic mass of hydrogen. I'm going to use the mass of a proton. And the mass of a proton is 1.007276. Over on the right hand side, I need the atomic mass of helium. That's 4.0026. But I need to subtract out, since this is the atomic mass, and I don't want the atomic mass, I want the nuclear mass, I do need to subtract out the electrons. That's going to be 2 times 0.000548. So that accounts for the helium nuclei that comes out, the alpha particle. Essentially, we've created an alpha particle with no electrons. Then I have the mass of 2 positrons, but it turns out the positrons have the same mass as the electron. Hopefully that makes sense to you. They're identical particles except for their charge. This has a positive charge, the electron has a negative charge. So ultimately, these 2 guys will cancel out. Now the neutrino has a mass that would be something like 0.000000003. So because the mass is so tiny in comparison to the mass of the other 2 particles, we can ignore it. The mass of the positron does not show up until around the 7th or 8th place after the decimal. And since neither of these 2 numbers even shows a value in that decimal place, we can ignore the value of this guy. So on the left hand side, we're going to end up with a mass of 4.029104, and on the right side we have 4.0026. So notice this is smaller, 4.029 compared to 4.002. So this is smaller on the right side, as it has to be. The mass on the right side has to be smaller on the left side, or otherwise this reaction would never go. So as a result of the mass being smaller on the right, there is some energy is released. Most of the energy released is in the form of kinetic energy of these 2 particles right here. Not to mention that we are also going to release a gamma ray. So part of the energy is in the form of the gamma ray. The rest of it is, generally speaking, in the form of kinetic energy of the 2 neutrinos and the 2 positrons. So let's calculate the mass defect. That's 4.029104 minus 4.0026. And that gives a mass defect of 0.026504. And we can then use the Einstein's mass energy relationship to calculate how much energy does that correspond to. Because we know that this number of U's can be converted into energy through the following conversion factor. 1 U is equal to 931 MeVs. So if we multiply this by 931.5, we end up with 24.69 MeVs. Now that accounts for most of the energy, but there's actually some additional energy that we get from this reaction, and that is because when you produce positrons, when they come in contact with regular electrons, with regular matter, they annihilate each other. So this is a process we haven't talked about very much, but these guys, if they come in contact with regular matter, they will annihilate that regular matter, and the particles will disappear completely, and all that will remain is the energy. These guys actually annihilate. One positron runs into an electron, they annihilate each other, and they release a bright photon, a gamma ray essentially. Not this gamma ray. There's an additional gamma ray that's not being shown in this reaction because each positron will combine with an electron to produce 2 bright gamma rays. Now, how much energy do those gamma rays have? They have the full value of the energy. So unlike the protons which fuse together to produce helium and then a small portion of the mass is released as energy, these guys actually release all of their mass as energy. So this entire amount of energy here is actually going to get released in the form of a gamma ray. So we actually get the 2 positrons combined with 2 electrons, each one having a mass of 0.0005486 to produce the gamma rays. So besides this, we're also going to get 4 times the value of a so each of the electron and the positron have 0.511 MeVs. Multiply that by 4. And we get 2.044 MeVs. If I add these two together, this reaction releases 26.734 MeVs worth of energy. That's the total amount of energy released by the fusion reaction of 4 protons. Now, these are very small nuclei, so a relatively small sample, 50 grams for example, since each one of these 4 produces a total of 26.7 MeVs, this is going to be an enormous amount of energy when you consider how many protons there are, for example, in a star. And this is ultimately the process that's at work inside of stars. Now the question is, how do you manage to get 4 protons to get together when of course you know they have a tremendous repulsive force? And the answer to that question is very simple. Fusion only occurs at high temps. So it turns out that this simplest of fusion reactions, the proton-proton fusion to produce helium, only occurs at a minimum temperature of 10 million degrees Celsius. 10 million degrees Celsius is approximately 18 million degrees Fahrenheit. So this only occurs. So think carefully about what has to happen. Why are the high temperatures necessary? Because the protons will fuse together if they get close enough that the nuclear force can take over. So the trick is, you got to get them close enough to each other that the nuclear force can be felt. If they don't get close enough for the nuclear force to be felt, then they will be repelled by each other because of their electrostatic force, and they will push away from one another. So to get them up to the velocity necessary so they can get close enough for the nuclear force to bind them together before the repulsive force pushes them apart requires the particles to have a temperature of more than 10 million degrees. And at that speed, they will get close enough before the repulsion takes over that they can actually be locked in by the nuclear force. Now, what about if you go for the next step, where you take, for example, a helium nucleus? So the next step actually goes something like this. We take 3 helium nuclei and we go on to produce a carbon-6. Now, these guys have 2 protons. So where, as you can imagine, bringing 2 protons together is very difficult, well, think about bringing 2 nuclei, each of which already have 2 protons. They repel each other even more, with more strength. So it turns out that this process doesn't occur until a temperature of almost 20 million degrees Celsius. It requires a much higher temperature, and of course each successive step you're fusing helium nuclei to bigger and bigger nuclei with a stronger repulsive power, and so as you can imagine the temperatures get higher and higher and higher until finally you reach the end product. The last fusion step is iron. Iron is the last step. And why is that so? Well, let's take a look. So if we make a graph of binding energy per nucleon, and down here we put the atomic mass number. If you remember, the shape of that curve looked something like this. And there was a point where I reached the maximum binding energy, the maximum amount of energy per nucleon. This guy, which rests in that location, is the most tightly bound nucleus in the entire universe. No nucleus is bound more tightly. This is the most difficult guy to break apart, and that turns out to be iron. So as we move up the ladder, fusing the particles together creates a more tightly bound nucleus, but once we reach iron, they cannot be bound any more tightly. This is the most tightly bound nucleus, and so therefore at this point the fusion process stops. So on this side we have a natural process called fusion. That's to the left of atomic number, not atomic number, but mass number 56, and on the right side we have a fission process. Take a look at what happens here. By going in this direction, we're actually breaking nuclei down, and that actually is improving the binding energy per nucleon. Notice that the binding energy is going up. We're getting higher and higher and higher as I break these nuclei down into smaller and smaller nuclei until I reach iron. And at that point, I cannot undergo the fission process and produce energy. What happens if you go in the opposite direction? What if you start at a point here and you move down to a point down here? Or let's say, for example, you start up here and you move to a point down here. These two reactions are not natural. What I'm going to have to do is I'm going to have to add energy. I'm going to have to add energy. So these reactions will not go unless I basically supply the extra energy. Now that's not a natural reaction. The natural reaction is to either fuse elements together to produce energy or to undergo the fission process to produce energy. But to go in the opposite direction, to produce fusion beyond iron, requires me to add energy. By contrast, to undergo fission below iron also requires me to add energy. So these are not natural processes. The natural process is to lead up in this direction through fusion, or to lead in this direction through the fission process. So this is where this graph is extremely important that you understand. how is it that I can fuse particles together and get energy, and I can break particles apart and get energy? It would seem like I could just fuse them and break them apart and fuse them and break them apart, and every time I do that I would get energy. Well, that violates the law of conservation of energy. The reason why I can do fusion and produce energy and do fission and produce energy is because there is this breaking point. Fusion works to the left of the line, fission works to the right of the line, but on this left side, fission does not produce energy. It actually sucks energy out of the system. On this side, fusion does not produce energy. It actually sucks energy out of the system. So this table is really important that you understand. If you have any questions, you should make sure that you ask about it in class. And again, this process over here is what's occurring in stars, and so the last product that a star will produce up until the end of its life is iron. Stars will not naturally produce anything heavier than iron, because if they did, if they started to produce anything heavier than iron, that would start to draw energy out. It would suck energy out of the star. It would lower the temperature of the star, and as a result of lowering the temperature of the star, the fusion reaction would decrease to the point where it stopped. Now, up until that point, the fusion is releasing energy, so as it releases energy, of course, it increases the temperature of the star. It makes it even easier for the fusion reaction to go. But beyond iron, these reactions begin to suck energy out of the star, and therefore it kills the nuclear reaction, causes the reaction to slow down, and then we end up stopping. So the most massive stars in our universe have a big lump of iron basically at their core, and that's their end product.